Okay, so here's a question that your textbook never actually answered. You have been using sine and cos for years. But why do they never go above 1 or below -1? Nobody explains this. Until now. In this video, we are going to figure it out together. And I promise, once you see it, it is going to make complete sense. It all comes down to one simple idea called the unit circle. Before we get to the big answer, let us quickly make sure we are on the same page about what sine and cos actually are. Because most people memorize the formula without really getting it. So here is a right triangle. You have got 3 sides. The longest side, the one opposite the right angle, is the hypotenuse. The side going up is the opposite. And the side along the bottom is the adjacent. Now sine of theta is simply this. The opposite side divided by the hypotenuse. That is it. Just a ratio, a fraction. How tall is the triangle compared to how long the diagonal is? And cosine of theta is the adjacent divided by the hypotenuse. How wide is the triangle compared to how long the diagonal is? 2 simple fractions. That is all sine and cosine really are. But here is the question that should be bugging you right now. If sin and cos are just ratios of a triangle, why are they always stuck between -1 and 1? A ratio can technically be anything. So why the limit? This is where the unit circle comes in. And honestly, this is one of the most beautiful ideas in all of mathematics. So pay attention to this part. The unit circle is just a circle drawn on a coordinate plane, with its center at the origin, and a radius of exactly 1. That is the only special thing about it. Radius equals 1. Simple. Now here is the key insight. Pick any angle theta. Draw a line from the center of the circle outward at that angle until you hit the edge of the circle. That point where your line meets the circle has an x-coordinate and a y-coordinate. And here is the magic that changes everything. That x-coordinate, that is cosine theta, and that y-coordinate, that is sine theta. They are literally just coordinates of a point on this circle. Watch what happens as the angle changes. The red dot spins around the circle. The teal dashed line shows the width, that is cosine. The red dashed line shows the height, that is sine. They are just measuring where the dot is on the circle. And as the dot goes all the way around, cos goes from 1 to 0 to -1 and back. Sin does the same but vertically. They keep cycling, round and round, forever. Okay, so now we can finally answer the big question. Why can sin and cos never go above 1 or below -1? The answer is actually obvious once you see the circle. The circle has a radius of 1. The dot is always on the circle. So the x-coordinate of the dot, which is cosine theta, can never be further than 1 unit from the center. And the y-coordinate, sine theta, same thing. Think about it this way. Sin theta is the height of the point on the circle. But the circle only goes 1 unit up from the center. So sin can reach 1 at the very top. But it absolutely cannot go any higher. The circle is the wall. Same for cosine. It is the width of the point. The circle only goes 1 unit to the right. So cosine reaches 1 on the right side, and it cannot go further. And on the left side, it hits -1, and it cannot go further that way either. Now here is something really cool. If you take that spinning dot on the unit circle, and you track its height over time and plot it on a graph, you get the sine wave. That beautiful S-curve you have been drawing for years. Look at this graph. The horizontal axis is the angle theta, going from 0 to 2 pi, 1 full rotation. The vertical axis is the value of sine or cosine, and you can see these 2 purple dashed lines at +1 and -1. The sine wave, in red, starts at 0, rises up to 1 at 90 degrees, comes back down to 0 at 180 degrees, goes all the way down to -1 at 270 degrees, and returns to 0 at 360 degrees. 1 complete cycle, and the maximum is exactly 1. not 1.1, not 1.001, exactly 1. Because that is the top of the unit circle, the wave hits the purple boundary and turns back. It cannot go through. Now the cosine wave, in teal, does the same thing, but it starts at 1 instead of 0. Because at angle 0, the point is at the rightmost edge of the circle, where x equals 1. Same shape, just shifted. Both waves are completely trapped between those purple lines. -1 at the bottom, plus 1 at the top. That is not a coincidence. That is the radius of the unit circle showing up in the graph. The geometry and the algebra are saying the exact same thing. Let us now look at the key properties of sine and cosine side by side, because there are a few things worth knowing cold. The range of both sine and cosine is -1 to 1, always. For every possible angle, no exceptions. That is the most important property, and now you understand exactly why. The maximum value of sine is 1, and it happens at 90 degrees, when the dot is at the very top of the circle. The maximum of cosine is also 1, but it happens at 0 degrees, when the dot is at the far right. The minimum value of sine is -1. At 270 degrees, the bottom of the circle. The minimum of cosine is -1 at 180 degrees, the far left. Notice how the geometry of the circle maps directly to these values. At 0 degrees, sin is 0 because the dot starts on the x-axis, so there is no height yet. But cos is 1 because the dot is at the rightmost point. At 90 degrees it flips. Sin is 1 and cos is 0. And both sine and cos have a period of 360 degrees, meaning they repeat the same pattern every full rotation. The dot goes around the circle once, and the wave completes one full cycle. And here is the bonus formula that connects both of them. Sin² plus cos² always equals 1 for every single angle. This comes directly from Pythagoras, because x² plus y² equals r², and r is 1. Now let us look at the special angles, the ones that come up in every exam, every problem, every real-world application. If you know these values by heart, trigonometry becomes so much easier. At 0 degrees, sine is 0, cos is 1. Easy. The dot is at the rightmost edge. No height, full width. At 30 degrees, sine is 1/2, cos is √3/2. At 45 degrees, both sine and cos equal √2/2. This is the perfectly balanced angle where height and width are equal. At 60 degrees, sine is √3/2 and cosine is 1/2. Notice how 30 degrees and 60 degrees are mirrors of each other. The sine and cosine values just swap. That is not a coincidence. Those are complementary angles. At 90 degrees, sine reaches its maximum of 1 and cosine drops to 0. The dot is at the very top of the circle. Full height, no width. Look at the pattern in the sine column. 0, half, √2/2, √3/2, 1. It goes from 0 to 1 smoothly. And the cosine column does the exact reverse, 1 down to 0. They are mirror images of each other across the table, and every single one of these values, without exception, sits between -1 and 1, because they all come from that same unit circle. The geometry never changes. All right, let us wrap it all up. Here is the big picture that I want you to walk away with. Number 1, sine and cos come from the unit circle, a circle with radius 1, centered at the origin. That is the foundation of everything. Number 2, sin² is the y-coordinate, the height, of a point on that circle. Cos² is the x-coordinate, the width. They are not abstract functions. They are physical measurements of a point moving around a circle. Number 3, the radius is 1. So the height and the width of any point on this circle can never be more than 1 unit, which means sine and cosine can never exceed 1. The circle itself is the constraint. Number 4, that is exactly why the wave stays between -1 and 1 forever. It is not a rule someone made up. It is a direct consequence of the geometry. The circle forces it. If this made something click for you, and I really hope it did, make sure you subscribe, because we are going to keep doing exactly this, taking the concepts that confused you in class and showing you the why behind them. See you in the next one.